So today we're going to just run through kind of an overview of everything in terms of linear functions. This is section 1.1 of your textbook. So first off, increments. We see this delta x, which represents the change in x values over a given interval. We use the same notation for y or any other variable, and this helps us define slope. So oftentimes you'll see delta y over delta x as rise over run, or m for slope. And if the slope is a constant, then that means we have a linear function. Now there's a few different types of equations that you see with linear functions, ax plus by equals c. If you see an equation written in this quote-unquote standard form, you can find the slope in one step by doing opposite of a divided by b. That's a nice little shortcut that a lot of people don't know. They usually take the time to isolate the y. More commonly, you'll see point slope form, y minus y1 equals m times x minus x1, where the coordinate x1, y1 is some point on the graph, and m is just the slope. You can alternatively rewrite this equation by adding the y1 to both sides. The advantage of that is it kind of gives you a calculator-friendly form. The other form, of course, is your slope-intercept form, the nicest possible form, where b represents your y-intercept on your graph. This is the easiest form to work with and graph with. So you should be familiar with all that information. That should be review at this point as you're entering calculus, but just good things to hold on to. So let's transition into talking about parallel lines and perpendicular lines, because we've worked with these over the years. We know that parallel lines mean that two lines have the same slope, so I've got a couple of parallel lines right here. The slope could be the same positive number. We know it's positive slope because the rise over run would be positive. As you go up, you go to the right. Perpendicular slope means that the slopes are opposite reciprocals of one another, and the intersection between the two lines form a right angle. That was not a very good right angle that I just drew, but we're going to go with it. So a common type of question that you might see in calculus could be they give you a function, you'd find a point on the function, and you could be asked to write the equation of a line that's parallel or perpendicular to a tangent line going through that point. So we just want to be familiar with all that. And just for clarification on opposite reciprocal, let's say that the slope of that line, we'll call it m1, is 4/3. We'll say that the slope of the other line is negative 3/4. Opposite means that you are changing the sign in front of the number, so from positive to negative, and reciprocal means that you're flipping the fraction upside down. Now let's transition into solving equations. So the first type of solving strategy that we're going to look at today is substitution. So there's primarily three methods: substitution, elimination, and graphing. Substitution is the one where you take a system of equations and you pick a variable in either of the two equations and you try to isolate that variable. So in this example, if I tried to get the x by itself in the second equation, I'd move the 3y over and then I'd divide by 2. That would isolate the x for me and allow me to plug it back in or substitute it back into the first equation. And then you could proceed with the solving steps. You would have the first equation written in terms of just one variable y. You'd be able to solve for y, plug that back into either original equation and get x. It's a fairly straightforward process, so we're not going to go through that specific process today. Elimination, similarly, we're not going to go through it step by step, but just as a quick review of how to approach it, you have to choose a variable, either the x's or the y's, and the idea is that you want to get the same number as a coefficient in front of either the x's or the y's. In this case, let's say we choose the x's. Right now, the coefficients are 3 and 2. I need those to be the same number, regardless of sign. One could be negative, one could be positive. It's totally fine. So I'm going to shoot for a 6. I'm going to multiply the top equation by 2 and the bottom equation by 3. That's going to allow me to end up with 6x in front of both, or a 6 essentially in front of both of the x terms. So when I multiply the equations, make sure you multiply on both sides. Common mistake, people miss multiplying on the right-hand side because it's just a constant, but you do have to do it. I multiply the top equation by 2. Hopefully I can do the math right. 39 times 2, I'm pretty sure 78. Multiply the bottom equation by 3. Excuse my terrible writing. It is tricky writing on the iPad. So I have a 6x in both equations, and what that allows me to do is I can actually combine these equations together to eliminate the x's. So I'm going to choose to subtract the two equations because they have the same sign. 6x minus 6x is 0x. Negative 10y minus 9y is negative 19y, and I can subtract on the other side as well. You could then proceed with your solving steps. You could solve for your y, you could solve for your x, but that is the general setup for elimination. Now let's look at that solution that we end up with, that x comma y. You guys have to keep in mind that when you're solving systems of equations, your solution represents the intersection point on a graph between your different equations or your different functions. So if I have this theoretical graph right here, where we've got these two lines that clearly intersect at a point, that point of intersection is x comma y. That is the solution that I would get if I solved these two equations either using substitution or elimination, or just opening up Desmos and taking a peek at what that point is. So that is solving by graphing, just identifying wherever that intersection point is. Now, there are some special cases when you're solving systems of equations, whether it's graphing, substitution, or elimination, because it depends on what the behavior of the lines is. You know, these lines were intersecting in my first case, so I have a clear solution, but that doesn't always happen. You know, you could have two lines that are actually overlapping one another, which is what I'm going for in my second picture. You can see I've drawn two lines directly on top of each other. So if you're solving that equation, you're going to get more than one solution because there's an infinite number of points where those lines intersect. Similarly, you can have a situation where your two lines never intersect. You know, you could have two parallel lines. So if you were to solve that system of equations, you wouldn't be able to get a solution because there's no place where they intersect. So again, if you have the same line, that's your first special case essentially, as opposed to having parallel lines, which is another extreme special case. In the case where there's the same line, you have an infinite number of solutions. Excuse my shortening of solutions right there. And for parallel lines, you have no solutions. One common question that we get with these different cases is, can I write all real numbers as a solution for the same line case? You know, is all real numbers interchangeable with infinite solutions? And what I say to that is no, not in this context, because the infinite solutions here are because we have an infinite number of points on the two lines that are overlapping one another. So there's points like 0, 1, 1, 2, you know, they have specific coordinates that you could list, but not every single point that exists is a solution. I mean, you can look at the picture that I have in the middle there, and you can tell 0, 0 is definitely not a solution to that system of equations. So I would say that it's wrong to say, for the same line case, that you have all real numbers as an answer. It doesn't really fit the context of what the answer looks like. So instead we say infinite solutions. I hope this video helped refresh your memory on linear equations as you review prior to calculus.